In this mini lecture, I'm going to talk about parabolas a little bit. So, first of all, the definition. A parabola is a set of all points in a plane that are equidistant from a fixed point and a fixed line. So, equidistant, that means the point is a certain distance from this point that's on the parabola is a certain distance from this fixed point, and it's the same distance from a fixed line. The fixed point is called the focus of the parabola. The fixed line is called the directrix. So we would have this focus here, that's this red dot, and then the directrix is this horizontal line, and we're setting it up sort of this way, and we've got these points in that are equidistant. There's this one point sort of directly in between. That distance from the focus or the directrix are labeled with this little 1 slash there. It's also labeled with P. Obviously then this point right here in the middle, that's called the vertex actually of this parabola. But here's another point up here. Notice if I take the distance from the focus to that point and then the distance from that point down to the directrix, so that makes a right angle, those distances are equal. That's labeled with sort of 2 slash marks here. This point here, the same thing. If I do that distance from the focus up diagonally to this point and then drop down directly to the directrix, those have the same length, and we've got this one over here on the other side. So we've got this idea that all these points on this parabola have the same distance to the focus as they do to the directrix. And we call this distance from the vertex to the focus P. That's also then the distance from the vertex to the directrix. So we're going to consider a vertical parabola like this one. Vertex is here at 0, 0. The focus is at 0, P. My directrix then would be y equals negative p, because we're going p up to the focus. We'd have to go down p to the directrix. And the key idea then is that the distance from any point xy to the focus must be the same as the distance from xy to the directrix. One thing I just want to add to this label then, what would be the coordinates of this point right here? Think about that a second. What would be its x coordinate? What would be its y coordinate? Remember, the x-coordinate is how far left or right it is from 0. So if we look at this here, if we start at the origin, how far left do we have to go to get to this point? Well, it's the same horizontal distance as this point up here, so it must have the same x-coordinate. So its x-coordinate must be x, same as the point above it. And its y-coordinate, well, that's how far up or down it is from the origin. And this is on this line, this horizontal line, y equals negative p. So its y-coordinate must be negative p. And so I'm going to set these two distances equal. If I do the distance from xy to the focus, I subtract the x-coordinates. That's going to be x minus 0, and then y minus p. That's what we get here. For this distance, I subtract the x-coordinates. That's going to be x minus x, and then y minus negative p, which is what I have here. So, of course, anything minus 0 is just itself. Anything minus itself is 0. Minus a negative becomes a positive. Of course, 0 plus anything is just itself. The square root of something squared, that cancels out. Then I square both sides to get rid of this square root, so I end up with something that looks like this. I would have to do some FOIL here. I didn't show the details. I'd have to take y minus p times y minus p and see what that's equal to, and then y plus p times y plus p and see what that's equal to. Those little details are left out. You can do those on your own off to the side if you'd like. We end up getting these results. When we look at this, we see that we've got a y squared on both sides, and we've got a plus p squared on both sides. So I could subtract y squared from both sides and p squared from both sides, and those would cancel out. So I'd be just left with this. I can add 2py to both sides and get something like this here. And that then is, we call standard form for the equation of a vertical parabola. So its vertex is at the origin. This p, remember, is the distance. How do I get from the vertex to the focus? We have it set up here so that P is positive, so the focus is above. If the focus were below, when I had this equation, this number in front of Y would end up being negative, and that would tell me that it was opening down instead of up. If we did this same development, but we started with a horizontal parabola, so the vertex is at the origin, but then I move to the right to get to the focus, the variables just sort of switch roles, and we get y squared equals 4px. So it still would have vertex at the origin. P, though, now would be how far I move horizontally to get to the focus, and the parabola would be opening right or left. If P is positive, it would be opening right. If P is negative, it would be opening left. Just like with ellipses and hyperbolas, for those I had a center that I changed. Parabolas don't really have a center. They have this point called the vertex. If it's not at the origin, if it's at the point hk instead, just like we had with ellipses and hyperbolas, the x squared gets replaced with x minus h, and the y squared gets replaced with y minus k. So one of the important things to remember here, one of the things to keep track of is the difference between a horizontal parabola and a vertical parabola, and it's really which variable is squared, right? So if y is squared, it's horizontal. If x is squared, it's vertical. For ellipses and hyperbolas, they were both squared, right? If they were both squared and they were added together, that was an ellipse. If they were both squared and they were subtracted, that was a hyperbola. If you only have one squared variable, that tells you it's a parabola and not the others. So here we've got this equation. Of course, the vertical parabola is exactly the same, except the x's and the y's have been switched. P is greater than 0, it opens to the right. P is less than 0, it opens left. That makes sense. With vertical, it also makes sense. Greater than 0 is up, less than 0 is down. For our vertex, for both, it's just this value hk. Remember, though, you've got to look at the x-coordinate to find h. So for this horizontal parabola, the x-coordinate is over here on the right. For a vertical parabola, it's over here on the left. But you just look for the variable. For the focus and directrix, it's a little bit different then. My vertex is here at this point hk. For a horizontal parabola, I have to move p horizontally to get to the focus. So the x-coordinate changes from h to h plus p. The k-coordinate stays the same. Of course, if it was opening left, this p value would be negative. So when I do h plus p, that would be h plus a negative number, which would be subtracted and would go the other way. The directrix is always the opposite way from whatever the focus is here. So if I'm adding p to get to the focus, I'm going to subtract p to get to the directrix. And again, it's the x-coordinate that's changing when I'm moving to the left. This idea of the focal length I'm going to talk about on the next page. The focal length for both is 4p. Here for vertical parabolas, notice the difference is when I'm moving to the focus, the y-coordinate is changing. The h stays the same, the k changes. And when I'm going to the directrix, the same thing. The y-coordinate is what's changing when I'm going there. For a parabola, there's this sort of funny named thing called the lattice rectum. It's a feature of the parabola that can be really helpful in graphing it. So the lattice rectum is the line segment parallel to the directrix. It extends across the parabola through the focus. Something else I really haven't talked about, these parabolas have what we could call an axis of symmetry. Right? If I go back here, we could add that in to this image here. The axis of symmetry goes directly down the center of the parabola, through the vertex, through the focus, and it's perpendicular. It makes a right angle with the directrix, right? It's perpendicular there. And so when I'm talking about this lattice rectum, the axis of symmetry would be going through the focus and the vertex. the lattice rectum is perpendicular to that. That's parallel to the directrix, which would be here below the parabola. And so I want to go, to get the lattice rectum, I go from the vertex to the focus, and then I go to either side here with a vertical parabola until I hit the ends of the parabola. We can actually show that this line segment going across always has length 4p. I put it in absolute value bars because remember, p can be negative, so we don't want a negative length here. That's why we've got the absolute value. And since the focus here is going to be in the middle, that means 2p has to be on either side. Now, the way we can show that, if we have this vertical parabola, it has to have the equation x squared equals 4py. But to be on the lattice rectum, it has to be at the same height as the focus. So that means it has to have the same y coordinate. These 2 points have to have y coordinates of p. The 2p, I don't know that. That's what I'm developing down here. But I know these p's have to be there for this to be at the same level as the focus. So I just substitute, instead of writing y in the equation, I write p. That makes it have a y coordinate of p. When I take the square root, I have to throw in plus or minus, so that's where I get this x is either positive 2p, that's over here on the right, or negative 2p over here on the left. And when we do some examples, we'll see that that really helps us get the graph really quickly here. There's also a reflective property of a parabola that's incredibly useful in a bunch of applications. It can be used in sort of 2 directions. First of all, if I start here at the focus and I have a beam that goes from the focus and hits the parabola, it gets reflected off so that it's parallel to the axis of symmetry, no matter which way it starts. Okay, or we could say that's perpendicular to the directrix. Okay, this is used when designing, for instance, light bulbs for flashlights or a car's headlight or something like that, where we would have the light bulb at the focus, and then we'd have a parabolic mirror behind that light bulb so that the light rays from the bulb hit the parabola and then go out in a straight line. That makes the light beam much brighter than if the beams were just going in all directions. Also, of course, that's why, you know, that car headlights can be directed up or down. There can be changes made to that for high beam or low beam and that kind of thing. The process can be reversed as well. If we have a beam that starts out and it's coming into the parabola, as long as it's coming in parallel to the axis of symmetry, when it hits the parabola, it gets reflected directly to the focus. That's sort of why it's called the focus, right? It focuses the beams in that way. The beams get focused into that one point. This is used when designing certain kinds of solar collectors or satellite dishes. So for a solar collector, for instance, this parabolic, it might be a reflective surface like made of metal, but it would be maybe a trough. So this would be the cross section. And then you'd put a pipe going through where the focus is, and in that pipe you'd maybe just have water going through the pipe that would be pumped through. The sun's beams, as long as they're coming in parallel, would get reflected to that pipe and heat up the water and eventually turn it to steam. And then that steam is used to turn turbines that generate electricity. That's actually a much more efficient way of generating electricity from the sun, much more efficient than the photovoltaic cells that you might have on a roof of a house. Heating up the water and having steam drive a turbine or something like that. Of course, it's important that the sun's beams are parallel to this axis of symmetry, so throughout the day that trough would have to turn and follow the sun. And you can see that sometimes out here in the California deserts. This is also used for satellite dishes. The beams coming in from the satellite come in parallel to the satellite dish. And if you've ever looked at a satellite dish, there's this little contraption that's up just a little bit from the bottom. That's the receiver. That's what receives the beams from the satellite. But of course the beams get focused by this satellite dish. That's also why the satellite dish has to be aimed in a certain direction so that the beams coming in from the satellite are parallel to the axis of symmetry. If that works, then the beams really aren't all that strong in and of themselves, but because of this focusing procedure, that's where that receiver has to be located. So if you're designing a satellite dish, you would need to know this property of a parabola.